Good morning, everyone. We're very excited to welcome you to our first speaker of the spring speaker series that we're hosting here in the Central Virginia node of CCI. Today, we'll be hearing from Dr. Nibir Dhar. He is a distinguished professor at VCU in the College of Engineering and a CCI Eminent Scholar. His expertise is in semiconductor research, particularly in electro-optic and infrared applications. Dr. Dhar is also an SPIE and Optica Fellow, and beyond academia, he co-founded iDisplay, championing STEM education. With 33 years leading EOIR technology for the U.S. Armed Forces, he's now shaping the future at VCU, aiming to build a center of excellence in EIOR tech for diverse sectors. Today, we'll hear more about the research that he's focused on in the future of infrared technology, and I will now turn it over to Dr. Dhar.
Oh, thank you for inviting me for this presentation. I'm really thankful for this opportunity. Let me share my screen first. So what I will be discussing the future of infrared technology and briefly also talk about some research, workforce, and education. Of course, infrared technology is a very vast subject, and there is no way we can cover the entire thing. But I'm going to point out some of the things what I see that will drive this technology in the future. So what really is interesting, Jonathan Swift's statement that vision is the art of seeing what is invisible to others. And infrared is literally what you can see, which is invisible to human eye. And advances in infrared technology, the primary areas really are listed here, but there are many, many things that are going on that will advance this technology. The key point of the advancement is that the primary user of infrared technology is military right now, the worldwide. So particularly, most of the development was done by US military and UK and France, but it's used in military. But I see the future where this technology will proliferate in various sectors. It's already in many sectors, including medical, transportation, agriculture, and so on and so forth. So I want to make a quick comment on imaging. If you look at what this is called is Kafka ring, if you look at this ring, which looks same color, same shading, but if you separate them, you see now the shading changes all of a sudden. So this is really a perception. What I'm pointing out is the imaging is very contextual. So what is the context and how does your brain function? At the end of the day, it doesn't matter what imaging system you do, you really, at the end, humans are observing it and how your visual cortex manipulates it, the perception, etc. So that's just some comment on imaging. But imaging is ubiquitous, meaning that it is used in pretty much in every area. And CCI, where you have CPS system, etc., where the sensor end will be imaging system, imaging components. And it's true for infrared as we go into the future. And all these different technologies that are being developed actually helps that. So the intersection of network, image sensor, and embedded computing, you can call that as an edge computing, is actually driving this technology for new infrared imaging products. So looking back in the history, really the discovery of infrared, it was done by Frederick Herschel, in 1800. What he did is he used a series of thermometers and looked at different visible light, because infrared you can't see. He didn't know about infrared. And as he looked at the temperature changes within these visible band from blue to red, he saw temperature increase. And then he moved his thermometer further and he saw temperature increased even more. And here he discovered infrared light. So technically, infrared, as you can see, is really part of the electromagnetic radiation. And it is considered something around a little bit longer than the visible band, like 800 nanometer, to something like 1,000 micrometer. But the usable range is typically up to 35 microns. These longer wavelengths are used in space. NASA uses them all. But in tactical range, in the more usable standard technology, is really goes all the way from something like 900 nanometer to some 15 micron. And what I'm showing here are these purplish color are what's called the transmission window. And all the other gray area is where the photons, the infrared photons, gets absorbed. So they don't go through. They get attenuated significantly. So if you look at the infrared technology, all the cameras are built around these windows so that you can see the photons. So there is transmission. And they have different nomenclatures. Air Force uses different, so the band, for example, 3 to 5 micron midwave, some may change that to longer wavelength and so on. But this is pretty much typical: shortwave, near IR, extended shortwave, midwave, long wave, very long waves, etc. So these bands are, important bands for Army, Navy, Air Force. So here's an example. For example, a galaxy, if you look at with visible, this is what you see. And in infrared, you can see more information. Of course, this is false color in the infrared imaging. And this explains a little bit better. If you look at a visible, where you have much better resolution, because the resolution is better when the wavelengths are shorter. So, but you don't know what's going on inside. When you look at the infrared, you can see the inside the bag, because the infrared radiation coming from his hands transmit right through. Another example is, this is the UK Leonardo DRS Celex. That company is rolling out a product where this game is called cricket, similar to baseball in some sense, is when a ball nicks the bat, and if you catch, the player is out. But many times ball is traveling very, very fast, and you may not be able to see it. But in the infrared, you can see the ball leaves an impression in temperature. So you can actually sense that the ball actually touched. So, there are a lot of advantages with infrared. The actual technology primarily was developed by DoD, Department of Defense, and in particular Army, where the various generation for the Army application, military application were developed. So we are now presently at 3rd gen, where it actually uses 2 colors, long wave and midwave. Midwave would have a better resolution compared to long wave. So with long wave, you look at a wide swath of area, and then with midwave, you can identify the target. So the question now is 4th gen. What is the 4th gen? So a lot of ideas floating around, and this is one area that we can brainstorm and think about what can be in the future. Here are some examples of different type of infrared detector design. This is like a innovative design for PN junction, whereas here you have superlattice design. Here's an NBN and so forth. There's a quantum well, microbolometer, and so on. This is your typical design in your cell phone for visible CMOS cameras. So the top row is what's primarily being used in the military. So in this point, I can say that the detectors, infrared detectors, can be divided into 2 areas. One is called the quantum or photon detectors, where there are interaction with the electron and holes. On the other hand, the thermal detectors, which are different design, which operates near room temperature. So where you actually deposit power and measure the electrical change within the system. So these are 2 primary areas. There are other areas happening, quantum dots and plasmonic, etc. So to make the system, you make the detector, whatever design you choose, and this little red square is one detector, and you make an array of detectors. Today, the largest array has been fabricated by Teledyne for NASA's Roman telescope that will be launched next year, or maybe this year sometime. And that has 300 million pixels. But what is the challenge in the infrared technology is having the sensor array or detector array that has to be mated with a silicon readout circuit, which reads the signal from the detector. So you can see there are different mismatch in the material. One could be a 3,5 compound or mercury cadmium telluride material. The other is typically silicon. And then there has to, in future, there's a lot of advancement, a lot of innovation going on. For example, to make a system, you have to cool this sensor. So you have the cooler, you will have all the electronic boards, you have the sensor, and then optics. Optics is also very interesting in infrared. It's very expensive. So you can see the whole thing is very expensive and could be bulky. So one of the trend is to eliminate the cooler. In that, and I'll show you an example, if you eliminate that, the cost, size, weight, power, etc., reduces significantly. So in future, innovations, of course, in all these areas are ongoing. Here's an example to increase the operating temperature of the sensor. We at VCU are working on a new design where we are trying to reduce the thickness of the absorbing layer. When you reduce the thickness, you have the advantage of low dark current or low noise. The bulk of the material actually creates these charges that are unwanted. If you thin that down, the disadvantage is that you will not absorb all the photon. So we are coming with innovative design in terms of meta surface, where we can increase the absorption by encouraging photons in lateral direction. So that's an example of research that we do. If we are successful, of course, this can operate at higher temperature, and ultimately cooling would not be needed. So advances on these 4 areas are of most important, and I'll talk about a few things here. But one of the greatest driver for the future technology is the digital ROI. So traditional technology uses analog, where you have columns or rows of detectors are measured and then transferred to a outside of the sensor area to multiplex and move the charges. And that is very slow, and it limits how much charge can you collect, because of the capacitor is limited by the unit cell size, the size of the detector area. So MIT Lincoln Lab has developed a new technology, and now it is becoming pretty matured, called the digital ROI, in where the actual charge, similar to CMOS imaging sensors, this readout circuit is able to, they are able to convert the charges into digital, from analog to digital within the pixel. And that have a lot of advantage. Once the signal from each pixel is digitized, now you can do multiple things. You can do various, you can move the charges wherever you want, you can do processing, all kinds of stuff. So that is a future advantage as the technology emerges. So ultimately, of course, the way I see it, we want to be able to make infrared technology in such a way that it enables imaging capability to deliver high value, salient, contextual, and intelligent data in various sectors, medical, defense, etc. And on the left, as you can see, y-axis is really the capability of the imaging system, and the x-axis is the computational complexity. As you can see, the complexity increases as we increase the capability. And therefore, the size, weight, power, bandwidth, etc., also increases. So that's the trade space, a challenge. And as the advances in artificial intelligence, microelectronics, all this that goes into the system, infrared system, improves, so can the infrared technology in the future will improve. And ultimately, we want one. This is like a model using human eye and visual cortex. Can we achieve that? Can we push all this capability, computing capability, etc., to the sensor plane? But of course, it has to come through various development. At VCU, we are looking at long-term. In the near term, of course, we want to create more innovation within the conventional design, but we want to be able to look at other materials, semiconductor materials, to make this new type of detectors and make innovation in the FPA architecture. Then we are also looking at, okay, how can we increase the operating temperature, as I just gave you an example, by various different thinning the design, using metastructure, and two-dimensional material, etc. Ultimately, of course, with collaboration with various other entities, we can look into 3D integration, neuromorphic, and ultimately make a scene inference image sensor. Today's image sensors are really morphological device, which really gives you variation in the intensity or the temperature differences. But you want to make it more intelligent and make the camera itself as a scene inference device. And for that, we are also developing modeling and simulation tools, various sensing modality, and so on, as we progress in our research. So in terms of scaling, I can talk about the scaling where in my past life, I have worked for DARPA, and one of my program, which is listed down here, where I adopted the idea where the cell phone cameras are used, how they are built. In thermal technology, this is uncooled technology, bolometer technology, the standard way is to actually manufacture the sensor chip, then separately electronics, optics, and then manually integrate them. So the process is slow. More importantly, it is expensive. But if you use this process, where we actually do wafer level camera production, and here you can see each of these are actually the camera sensor, and then you including the camera engine, all these electronics, and then all you do is add the optics at wafer scale. So here is an example of I don't know if you can see it. You see this is a iPhone, older version, of course, and has this long wave camera embedded in it. So that's a scaling of the camera system in uncooled. Similarly, we had programs at DARPA called the AWARE program for cool technology, where we scale the pixel to Nyquist limit. So the advantage of making pixel very small is shown in this graph. If you look at the sensor chip area in terms of centimeters square, and this is the swath of area or field of regard that you can see called field of view. So for the same sensor size, for larger pixel, let's say you have 500 by 500 pixels, in the same area you can fit 2000 by 2000 for a 5-micron pixel. The advantage is that when you look at this, at the scene, you are looking at very small field of view. But for the same size, you can look at much larger field of view. So you can see a bigger swath. As I said, imaging is contextual. You want to be able to see the environment to make a decision what that target looks like. And so here, for the same range, same size, you see much better, much more area. The other advantage, of course, is that you will, because the pixel is small, you can have a lot more dyes in a wafer, and therefore it will drive the cost. This development is progressing in the future for the military, where most of the technologies now are going after smaller pixel design. So here's an example of 5-micron pixel for 10-micron radiation. This was the world's first small pixel imagery that was developed by Leonardo DRS technology in Dallas, Texas. And you can see the resolution is significantly improved. It is HD. And as you can see, the edges are very, very sharp. Typically, edges are diffused in infrared imagery. The other scaling, in future is actually scaling from very wide field of view and very large number of pixels, like gigapixels. But the challenge, of course, is that when you scale to make, let's say you have gigapixel here, your optics will not sufficient. So information will be actually reduced. So that means anything greater, say, as you can see my cursor, greater than that will not be any benefit because there are a lot of geometric aberrations. So what we have done under that program, that was called DARPA Aware, where it is similar to a parallel computing system, where you actually make an array of image sensors, and then you actually process. So you collect the signal, then individually you have micro cameras, what called micro optical processors, and then you stitch it on the fly. So here's the camera, but it's still pretty big. But compared to, say, a large space-based telescope, it's still pretty small. And here's some imagery, as you can see, that because it's 120-degree field of view, typical infrared cameras are like, at best, 40-degree field of view. So now you can see the entire field. At the same time, individual cameras, you can either zoom in or see a region of interest. For instance, here, as you can see, all the way you can see the boot laces. So this is an advantage, and Navy is very interested in it, as well as the sports industry, because you can individually see the players within the entire field, which a standard camera will only see a small portion. Now, of course, to make that and scale it even smaller, some of the ideas that were floating around during my DARPA program, one is this, where you can actually have a ball lens, which then has a very wide field of view and actually has integrated lenses within them. And then you have a whole sensor array. You can make gigapixel cameras that can be even handheld if advances are made. So this is future advances will be so-called the high space bandwidth product design. The other area that the future of infrared technology depends is what we call sensing modalities, meaning how do we sense the scene and incorporate and then produce the image. One is the computational camera, heavily used in the visible domain. Some areas people are looking into using infrared. The other area is called 3D integral imaging, where University of Connecticut, Dr. Javidi, has made significant progress, in which you can do projection and look at a 3D image. I'll say a couple of words afterwards. But the most important and really advantageous technology is called the compressive sensing, in which, let's say, I mentioned earlier gigapixel, I mentioned 300 million pixels infrared, but imagine the data that it will collect. It will go crazy, right? I mean, the processing, the lag, and all that will be horrendous. But compressive sensing is, imagine if you have a 1 million pixel, you, in traditional way, you actually sample 1 million samples in the scene. But in compressive sensing, you only sample the scene, say 1%, maybe 10%, and then you reconstruct mathematically. And there's a lot of progress going on. Then there is significant advantage if we can do that. The advantage of intelligence within the imaging domain, this chart kind of give you an example. So for example, military really loses many helicopters when they try to land in a sandy area because of what's called brownout, because it just kicks up all this sand. So no longer can you see the surface, and therefore it's challenging to land it. In this program, this was also my DARPA program, where we came up with some machine learning technique and artificial intelligence. And actually, I can only show you the simulation where you can see this, the same image, but here, because of the dust, you can't see, and here you can. So that's an algorithm called Lucky Look. In that algorithm, you can implement that and be able to. So currently, Army is doing a lot of tests on that. The other area within this is, in the future, is to be able to extract image or target within a very noisy scene. So this, you can literally not see the scene, but with some interesting algorithm, you can actually extract it. And you can see there is a person. So these are the future areas of advancement in the infrared technology. Another area that the future is going to see is actually of course, artificial intelligence, machine learning. So you can learn, say, in this particular project, what we were looking at, an infrared image, and see if you can match it with a visible image. So the challenge, of course, here is that in a machine learning, you have to have a lot of data to train your system. And in the visible domain, you have trillions of images. You just do a Google search and you'll find so many images. There are big databases. But in infrared, you don't have that luxury. So it's called domain transfer, where we try to learn from visible data and infer infrared from there. And at the end of this project, actually, when we did that, initially it was 39%. So if I look at the infrared image, you cannot even tell. But if you try to match with the visible, 39% match. But then at the end of that project, it was 60%. So this is another area that we want to do. So for this, we are actually developing or will be developing an Unreal Engine that we can use, which is typically used for visible gaming industry. If we can use that and to create infrared imagery, infrared scenes, infrared-based human faces, and so on, then we will have the training data. That's one of the idea there. Another area which is very important to military is the automated target recognition. So if you look at a very cluttered scene in infrared, you see some interesting features, but you can't tell for sure. You want to use this technique of transfer learning and with using synthetic data in order to extract the targets within this. Like, where is the threat? We want to know, because it's so cluttered. And therefore, the future technology will really try to drive the intelligence within the imaging system in order to understand and extract targets. Another area that I think will move, and that is possible because of the digital ROIC, that you can in-pixel digitization allows you to now manipulate the signals in various ways. The embedded technology, so as I have given you an example of infrared embedded within a cell phone, it doesn't matter how big, if you can actually drive these technologies, particularly, say, in smart city, Internet of Battlefield or Internet of Things, etc. In this technology will actually get commercialized. If we can do this, CCI is very interested in these cyber physical systems, etc. Then actually commercial sector will actually adapt these things if you can drive the cost, weight, power, etc. down. So that's another area of future of infrared technology. So a last area that I want to talk about has not been realized, although within this area, DARPA has a couple of programs. For example, they had Real Imagine one program, where I think that is more of a driving technology with adding many layers of processing. So it's like 3D integration. But if we look into the biological system, human eye and visual cortex, that human eye does a lot of processing within the retina. And then the big brother, the visual cortex, actually does the big processing to infer the scene itself. It does some things like neighborhood pooling. It does inhibitory function. So if you do pooling, so you take neighborhood pixels and pool the signal, you get a different feature. We have done some studies in that. On the other hand, if you take the neighborhood pixel and suppress them, and then you can increase the signal to noise ratio of a given pixel. So there are a lot of different biological aspects can be brought into. If we can look at a design if you look at a photon that's coming from a scene, it carries many information. But in traditional imaging, all you use is the brightness or the intensity variations. Morphology, that's what I was talking about. But if you can harness all these different information within the system, then you can know a lot about the scene. For example, I think that it's possible to do with 3 layers. If you have an encoding layer, an optical encoding layer, then you have the detector, and then you have the processing layer or integrated circuit block. So with this kind of joint design, we can come up with a very intelligent system. So this is like culmination of computational imaging, integral imaging, compressive sensing, etc., putting them together into a system that can be very intelligent system. And for military, this would be very important, simply because the soldier has a job who's engaging with the enemy, but all the aiding tools that he uses, or she, the sensing system, for example, which can be intelligent and provide information rather than just the scene itself. So data fusion, I've shown this videos to in previously when I gave a seminar a few years ago. It shows you the advantage of data fusion. In this, we are only fusing visible, shortwave, and longwave, as I'll show you. But if you look at a parking lot scene here, you see some lights. You see very faintly see a person in the car. That's pretty much all the information you get. If you see the same thing in shortwave band, where it is like 900 nanometer to 1.7 micrometer, you can see the person very well. You can see some features, but remember there were lights here you couldn't see. And now if you go back to long wave, for example, which is cut off at, say, 12 micron, 8 to 12 micron, you can all of a sudden see this hidden person in here, the person here. Another thing, you cannot see the person inside because the long wave cannot go through the glass. But you can see that this car is actually hot here. That means the car was running, or it was running not a short while ago. So you can now tell the engine. So the point here is that for different visible bands and infrared bands, you get different information. If you intelligently fuse them together, as shown here, you can see all that information. Of course, you can improve this much more, and then you can use artificial intelligence for the imaging system to be even smarter, to understand all these different details, is also an area of future of infrared technology. Okay, so that's, I mean, there's so much more to talk about, but there is not enough time to discuss everything. So what I wanted to show here is that the future of infrared technology, one point I want to make is that as the technology improves, the cost, the size, the weight, and the power reduces, it will start to get into the commercial domain a lot more. It's still already there. For example, the transportation, they use thermal cameras for detecting animals and people. But in the medical industry particularly, this technology will be very useful if we can increase sensitivity, other technology areas, then it can be a great technology for, say, medical diagnostics, blood flow and things like the breast cancer and so on and so forth. It can be a great technology for agriculture, for example. Agriculture actually already using some of it, but the use of mass usage depends on the size, weight, power, and cost. And so that will happen. So now I want to shift gear a little bit and talk about, say, learning, education, and workforce, where you may have heard about the Convergence Lab Initiative recently was announced, in which we have 5 different pillars. Initially, this year, we are, invoking arts, quantum and photonics, microelectronics, AI/ML. And then next year, we plan to include biomedical, because biomedical is also very important in many ways for military. For example, wearable sensors and to look at vitals, etc. And then, of course, this is all supported by modeling and simulation. So this is a large program. As we progress, more focus on DoD, but it also has applications in commercial domain. Ultimately, we want to make this technology where it's commercially viable. In this program, we have a lot of education, we have workforce development program, etc. If you see that the 4 main areas of research are modeling and simulation, and then electro-optic and infrared, which is the area that I work, and then radio frequency and communication, and then finally edge technology. Edge technologies is very, very important because, you know, it is simply put, it's computation at very low size, weight, power, and cost, and without, say, cloud service. So you have to come up with new technologies within this. So all these 4 areas put together is what the idea behind the Convergence Lab. And there you can see all this technology will also benefit the infrared technology itself, because as you know, you learn lessons learned from these technologies will actually feed into the technology, as I showed you that trade space chart. In terms of workforce education, we have currently running 2 programs. One is called the Aspire program, that's funded by the Army, and the other called A-Star program, which is funded by the Air Force. Both are sort of complementary program. The Aspire is actually 12 university ecosystem with at least 5 universities that are HBCU-MI. And this A-Star program is actually 50 university ecosystem. So this type of ecosystem helps us to increase our collaboration, interaction with other scientists and engineers and professors and students. And the third area, which has not been launched yet, is for a veterans program called VA-STAR, where we are trying to develop certificate program and train our veterans. So while these veterans were working in the front end, now after becoming a veteran, they will work in the back end to help the technology for the military. So that's all I have. In the end, I put this beam me up, Scotty, because if you are a Star Trek, if you are a Trekkie, you have noticed that they have this infrared wraparound sensor on the eye, because he was this character was blind, so he can actually see with this infrared. So I think in future, infrared, and there is a lot of work already going in that sense, is to be able to give eyesight to the blind, offer new medical diagnostic products, help with agriculture, discover new galaxies, and so on and so forth. There's a whole myriad of applications within this infrared technology for both military and commercial. So with that, if you have questions, I'll be happy to answer. Thank you.
Thank you for that wonderful presentation, Dr. Dhar. We do have some questions coming from the audience, so we will first talk to Dr. Atulasima.
Yeah, hi, Nibir. Very nice talk, because I had looked at various aspects of it, but this is good to have everything in one place. I do have some questions. The first thing is the visible to IR. You are talking about the lack of images in the IR database, and you're trying to enhance it. So you're planning to do this experimentally by taking IR images of people's faces, or are you going to simulate what from a visual image, what the IR is going to be, and use the simulation to train your networks?
So at first we want to do simulation.
Okay.
Because experimentation is expensive. But once we do simulation and understand, and then we actually want to do real experiments where we are getting different type of imaging systems, where we can do not just human faces, but scenes and any imaging. with different bands in the wavelength. So from a simulation perspective, we're developing a model using the Unreal Engine is to see how we can synthetically develop a much more data. Worked in the shortwave band for the NATO company organization, where we were trying to develop a model for the shortwave band. There's a great model available within the visible band, but there is no model in shortwave, midwave, longwave. So we want to develop that and then use experimentations.
And then follow up some short questions here. You talked about situational awareness. Is that a public database or is it something that's not? Because if we have an AI tool that we develop, how do we test it?
So there are some military database available. We can access those database provided we have some sort of agreement. And in the past, I have done that. There is actually a database that I provided to VCU.
Sure. Sure. And one final question. This is about the TRL levels and demos. So from my experience, I understand that you can at VCU develop imaging technology where you can do it on thin films and eventually a patterned device. You can also do the processing technology on software, probably demonstrate it on an FPGA. But the biggest problem is integrating the two, because each time you want to do a CMOS tape out, even at 130 nanometer node or something like that, it's a huge hundreds of $1,000 cost. And then you're talking about heterogeneous integration with photonic technology. So what TRL are we and what TRL are we promising to deliver?
Okay, good question. Yeah. So first of all, for us, demonstrating a TRL on the order of, say, 4, maybe even 5, which is like in the laboratory demonstration. But remember, innovation will not happen if we just work ourselves. You have to work with industry. You have to work with other facilities. And that's exactly what I'm trying to create. In sense that because our goal is to educate and do research and demonstrate the idea in some sense, but we really need to bridge the gap, we have to work with industry. For example, we are trying to develop infrared optical communication. So we have identified one company who has interest in it, and so we will collaborate. But our goal really is to demonstrate the idea in whatever shape or form. And that won't go beyond TRL5.
Okay, thank you.
Great, thank you for those very insightful questions. Dr. Hadamani?
Hi, Nibir, great talk. So my question is related to the workforce development, and I see that you have added biomedical area as well. Is there a reason why there is a delay in including biomedical in either A-STAR or Aspire programs?
The reason we are not doing biomedical at this stage, simply because when we proposed this concept, that concept didn't have the biomedical at that time.
Okay.
And then I did some research and look into why biomedical would be so important for the military. And I did some discussions, and they said, yeah, biomedical would be interesting. But what happened is when we proposed this program, those 4 areas were locked in. So there was no budget given or requested for the biomedical. But going forward, definitely biomedical would be of great interest. In fact, if you're in the area, in the biomedical field, I have some ideas that I want to discuss. That includes biomedical physiology and infrared. So we should discuss about that. But hopefully, as we move forward, we will start to have projects within biomedical.
And that will be extended towards first capstone or A-STAR or VA-STAR. How is this? Or all 3 at once?
All 3, yeah, all 3. We can, the capstone program that 12 university program that we have are really focusing on Army relevant technology, right? So we, and therefore I was mentioning, we can start with capstone because that's a low budget approach. Next year we can actually do that, where we can involve, we need to discuss, why is it interesting to Army? We need to discuss, we need to come up with a project and then grow that project to a more substantial, with graduate students, that we can actually develop such a technology. So the focus of CLI is really driving such technologies that are of interest to Army, Navy, Air Force, particularly for Air Force, for instance.
Okay. All right, thank you.
You're welcome.
Dr. O.
So I sort of missed the front part of your talk, but one of the things that, Atul was mentioning, I kind of want to build on that, and that is, CLI right now is the Convergence Lab for lots of different diverse types of activities that hopefully will be like a unifying sort of center for a lot of stuff that's going on, not only in the College of Engineering, but broadly around the university and elsewhere. How difficult do you think it's going to be to pull together some of these, kind of again, organizations outside of the university? So you've got experience with the DoD, but let's just throw in there like Department of Energy or NASA, or typical people who I think would be open to the idea, but right now they're just hypotheticals, so to speak. But we want to move them beyond that stage. Okay. So anyway, that was my question: is how do we sort of kind of again start to converge on who the players are and stuff?
So Carl, thanks for that question. I think it's an important question. The idea of Convergence Lab is not necessarily related to just the Air Force technology. What Convergence Lab that I envision is actually a convergence laboratory within the VCU that is encompassing various interesting technology combination that can result into something. It so happens that Air Force funded us $9 million, but I'm looking at Convergence Lab as a big platform in which we want to develop other things. It is not owned by Air Force. We want to do various other things within it, but it's initiated by the Air Force, but we will grow it in various, whether I have been discussing with NASA and other areas, or we have like Oak Ridge, JPL, and other folks in different organizations. So we should not look at Convergence Lab as a DoD relevant. Right now, I put it as DoD simply because the funding is provided. But under the Convergence Lab, we can propose other things. We can do, it's a fertile ground for the entire university, particularly College of Engineering, where we can grow other areas and integrated areas and bring in many other folks, including industry.
There is one follow-up I would like to ask. So you were talking about the role that AI plays in the development of infrared technology. We talked about the compressive sensing and some of the simulation that AI might be playing a part in. And I'm curious how this particular focus area is trying to, let's say, insulate the AI you're using against the vulnerabilities that can happen with respect to bias in the training data that into the systems.
Right.
So can you speak a little to that?
Sure. So, like ChatGPT or even Google's backend and Facebook and so on, there's misinformation, disinformation, biasing, etc. The AI I am talking about is an unbiased AI, which is the actually interaction of the machine itself, not so much so those AI is to enhance the capability of the imaging system. For example, identification of an individual, like I get an example that I gave, or how system can actually aid humans. So it is quite upside down. Our AI approaches are really using the system to assist the soldier, or using the system to help the doctor, and so on. So it is not. So all these other, what you're referring to are textual based AI, like ChatGPT and so on, where you can introduce bias. In our AI, we cannot introduce human bias, I'm talking about. We cannot introduce human bias because it has no place in it. Its function is not relevant to them.
All right. Last call for questions for Dr. Dhar before we wrap up. Thank you all very much for attending. This is the first in our series of speakers throughout the spring. I'm going to drop a contact email in the chat. If you all have any follow-up questions or would like to connect with Dr. Dhar, please feel free to reach out to us in Central Virginia Node, and we'll be happy to connect you. Have a great day, everyone.